Hello, everyone, and welcome to Nunley Math. As always, I'm your host, Aaron Nunley. I want to thank you so much for joining us as we begin our discussion of solving systems of linear equation. We actually have three different methods for solving systems of linear equations. We're going to look at those in three separate videos, so we hope you'll come back and watch our other two as well. The first method was the kind that we consider to be the easiest to understand and probably the most work to do. We're going to work our way towards some easier methods that require a little more in-depth understanding. But this is a pretty good way to get started. We did just wrap up our linear equations unit in my Algebra 1 class, so I'm hoping that you have done the exact same thing. You will notice that I've got a quick review of some of the concepts from our linear equations unit here on this first slide. You'll notice that I have two linear equations written up here together. I'd like you to pause the video and take just a second to graph those on your own. I'm going to keep right on going, assuming that you have already done that. Since graphing is not the focus of this unit, but rather the idea of understanding systems, I may go through this a little quicker than you're used to. If you're having a little trouble following along with this, I would recommend going back and looking at our linear equations videos, and that may help you along the way. Notice this first equation is written in slope-intercept form, y equals mx plus b, where the number in front of x tells us the steepness of our line, and the number that's out here by itself tells us where our graph is going to cross the y-axis. So, since there is no number written in front of the x, we know that it is a 1, and the y-intercept is the point 0, 1. So I'm going to graph that. There's my y-intercept, 0, 1. My slope says go up 1, right 1, over and over again, so I'm going to do that several times. And then I can also go down 1 and left 1 because negative 1 divided by negative 1 is also positive 1. And then I draw my line that goes all the way through there. Now, you don't necessarily need to put as many dots as I do. I did that more for your benefit than anything else. Just keep in mind that you need that line to be straight, and a lot of times if you just have 2 or 3 dots down here together, sometimes even if you're using a ruler, they can get off the farther you go. So depending on how accurate your graphing is, you might need to do more dots than maybe you've done in the past. Let's go ahead and graph this second equation, 2x plus y equals 4. I notice that this is in standard form, ax plus by equals c. I do have the option of putting that in slope-intercept form if I wish, or I can graph it using intercepts. I think I'll do the latter. When we graph by intercepts, we say if I put a 0 in for the y, what would that be? Well, plus 0 would be a nothing, leaving me with 2x equals 4. I'd divide both sides by 2, and I'd get an x coordinate of 2. I then repeat the same thing with putting a 0 for the x. 2 times 0 is 0, which is essentially nothing, leaving me with y equals 4, so my coordinate would be 4. So I'm going to cross the x-axis at 2, 0, the y-axis at 0, 4. I can look at this and notice that that is a slope of negative 4 over 2 or negative 2 over 1. So I'm going to go through and just repeat that a couple more times. Here again, I'm doing this quickly because that is not our focus today. And then, of course, we draw our line through those points. Remember, every point along this blue line, every dot, every spot on that blue line is an x and a y combination that would make this into a true statement. Every point along this red line is an x and a y combination that makes this second equation a true statement. But that point right there is extremely significant. Do you know why? Hopefully you realize that this point right here, this point 1, 2, is the only point out of all the points on our graph that makes both of these statements true. If I put a 1 in for the x and a 2 in for a y, that makes the first equation true. If I take the second equation and I put a 1 in for the x and a 2 in for the y, you can see I've got a straight parentheses there. I'll go clean that up later. You'll notice that that is also true because 2 plus 2 equals 4. You see, when we talk about systems of linear equations, what we're doing is we're going to take two or more linear equations in the same variable. I would go ahead and circle that word same. The solution to a system is the ordered pair that is the solution to all, and I would circle the word all, the equations in the system. Since 1, 2 makes both of these equations true, it is the solution to our system. And that basically is the big idea behind what we're trying to do today. Most of the rest of this is clarifying a few small details and looking at multiple examples, but that's pretty much what we're going to do. We're going to graph both lines on the same coordinate plane, and we're looking for the one point where they cross, that one point that makes both those equations true. That's how we solve by graphing. You graph one, you graph the other, you find where they cross. I'd recommend pausing the video and trying this second one on your own. I'm going to go ahead and do this assuming that you have it already finished. Notice they're both in slope-intercept form. The first equation has a y-intercept of 5 and a slope of -2, or we should say more properly the y-intercept is the coordinate 0, 5 and has a slope of -2. So we start off at 5 and go down 2 over 1, down 2 over 1, and so on and so forth. Again, we're doing this quickly because graphing a line should not be our focus right now. Our second equation in our system has a slope of 4 and a y-intercept of 0, -1. So I start off at -1 on the y-axis, and I use my slope of +4 to graph my line. Notice once again, I have a single point that makes both of those true. It's the coordinate 1, 3. It's the solution to the system because it is the only point that makes them both true. I could test the first equation out by plugging a 3 in for y and a 1 in for 2. That, of course, works. And then I could put the second equation, do the same thing, put a 3 in for y and 1 in for x, and of course 4 minus 1 does equal 1, or does equal 3. So that is true as well. Not too bad, right? Tell you what, there are 3 things that can happen when we do this type of problem. 3 things that can happen when we do this type of problem. Number 1, we could see what happened on our last slide, and you will notice that you cross at a single point. Those kinds of systems have one solution. They are referred to as consistent, a system that is consistent. You'll notice that you could have 2 lines that end up being parallel. Those are lines that have the same slope but different y-intercepts. If they are parallel, they will not cross at all. They will have no solutions. We call those inconsistent. The last thing that could happen is you could have the exact same equation written 2 different ways. When you graph those, since they're the exact same equation, they're going to get the exact same line, and you will get an infinite number of solutions, meaning everything that works in the first will also work in the second. We refer to those as being dependent. Tell you what, why don't you take a second, try these sets of equations, these systems. I'm going to assume you've already done that, and I'm going to go ahead and do them for you quickly. Both of these are in linear equations that are in slope-intercept form, meaning I have a slope, I have a y-intercept, and I can graph it. The second equation, I have a slope, I have a y-intercept, so I can graph it. The solution to the system is 3, 1, because 3, 1 is the only point that works in both. Certainly you could check that on your own. We're not going to take time to do that today. These 2 equations are not written in slope-intercept form. They are written in standard form. This first one I could solve with intercepts. I actually don't think I'm going to do that because if I tried to do that, I think I'm going to get some decimal answers. So instead, I'm going to put this in slope-intercept form. Remember, I need to have y by itself, which means I need to get rid of this 2x that's added on. I do that by subtraction, and I end up with y equals -2x plus 5. Where I have a slope and a y-intercept. That's enough information to graph. The second equation, I'm going to rearrange by subtracting the 3x from both sides. You'll see I get negative 2y equals negative 3x plus 4. And then to get rid of that times negative 2, I'm going to divide both sides by negative 2 and get 3 halves x minus 2. Again, this is not the focus of the lesson today. If you're having trouble rearranging these, that is a separate video. But we do have a slope, we do have a y-intercept, and I can graph those as well. 2, 1 is your solution because 2, 1 is the only value that makes both the linear equations true. Now, you'll notice this time I did do something slightly different. Notice that this equation is already graphed. The reason it's already graphed is because it's actually the exact same equation from the last slide. What I have done is change this first equation, and you'll notice that I forgot to put in an animation here for the intercepts. So I'll just go ahead and tell you that I'm going to graph this by intercepts. I put a 0 in for y, x must be a 5. I put a 0 in for x, y must be a 5. And I can graph those points as well. Notice that once I graph my intercepts, I can see that it's down 5 over 5, and so I just continued that to get a couple extra dots to make sure that my line was straight. I draw that, and something really interesting happens. Notice that these two lines are parallel. Those are not going to cross at all. Notice they have different y-intercepts, but they both have the same slope of negative 1. Because of that, we say that there are no solutions. It is inconsistent. One last example like these. These are in standard form, so I am going to graph them with intercepts. Once again, I'm doing this pretty quickly because graphing the individual lines really is not our focus. In this case, you will notice that we have the exact same equation written two different ways, which means when you graph both lines, they end up in the same spot. In fact, if you wanted to, and if you were paying really close attention, you might have noticed that all I've done is use the property of equality to double both sides of this first equation. And that's how I created the second equation. I'm sneaky like that. Because they are the same line, any point that works in the first will also work in the second, so this will have an infinite number of solutions. We say that the system is dependent. By the way, I did not mention it earlier, but this symbol right here, this little set of braces, is one way that we identify a system. It just means that these two equations are working together. Couple other things I want to make sure you're aware of. Sometimes you might be asked to determine if a point is a solution to the system. Just keep in mind that the solution to the system is the coordinate that makes both of them true, which means I need to take the first equation in the system, plug in the 2 and the 5, and verify that it works. I need to take this second equation in the system, plug in the 2 and the 5, verify that it works. And as long as it works in both, then we would say, yes, it is a solution to the system. It's important to remember that if it works in one, that is insufficient. It has to work in both. Let's try this other one. We want to see if negative 2, 0 is a solution to the system. So I take the first equation, put a negative 2 in for x and a 0 in for y, and it works. I take the second linear equation, put the 0 in for y, the negative 2 in for x. It does not work. Negative 2, 0 is not a solution to the system. The last thing that can possibly happen is these could be given to you as application problems. Notice it says your family opens a bed and breakfast. They spend $600 preparing a bedroom to rent. The cost to your family for food and utilities is $15 per night. They charge $75 per night to rent the room. This story has two different pieces. It has a cost relationship. In this case, our cost is $15 per night plus $600 to set up the bed and breakfast, or more simply, C equals 15N plus 600. And then there's a revenue relationship. A revenue. Remember, revenue is income. We're told in this problem that we earn $75 each night. I could write that as R equals 75N. Now notice over here on the right, I have a graph set up. Notice that I have the number of nights along the bottom. Both of my equations use the number of nights, N for nights. I spend 15 per night on my customers, but they pay me $75 per night. And then notice that we have a cost revenue on our y-axis. We can list both those together because they are both ways of talking about money. One is money I spend, the other is money that I earn. Money I spend and money I earn. If I were to try and solve a system involving these two equations, for my cost or expenses, I would say my y-intercept is 600 and it grows at a rate of $15 per night. Now, I got tired of counting up by 15s because I think that's kind of awkward when your scale is by 50. So I said, hey, what about 10 nights? And I plugged that in. 15 times 10 is 150 plus 600. That gave me this point, and it saved me a little bit of effort as I was trying to get enough points to make my line. My revenue line says I start off with a y-intercept of 0. If nobody has stayed in my hotel, or if people have stayed in my bed and breakfast for 0 nights, then I've earned $0. But it goes up $75 a night. Now, I noticed very quickly that $75 a night is $150 every 2 nights, and that put me on, here on my intersections. So I started counting that way, and I got this line. Once again, we have an intersection of those two lines. This intersection is 10,750. It is the solution to our system. But more importantly, it gives us a lot of information about the business that we're in. It gives us a lot of information about the finances of this bed and breakfast, because this is called our break-even point. At 10 nights and $750, we have broken even. You see, we started off with a lot of expense back here on before we opened our hotel, but our expenses grew very slowly. We started off spending $600 right out the gate, but then we stopped that and started spending $15 per night on things like little soaps and laundry and clean dishes, I don't know, somebody to cook the breakfast. So our initial cost was very high, but our rate of growth on the cost was very low. On the other end, our income started off very low. People didn't give us money before they started coming, but it's growing at $75 a night. It's growing faster than our expenses increase, which means prior to day 10 and $750, we were operating at a loss. We had spent more money than we had gained. Over here on the right, we're running at a profit. Profit means not only have we brought in as much money as we've spent, we've brought in more money than we've spent, and that's money we get to keep to feed our family. Here's another example kind of like that. A roofing contractor buys 30 bundles of shingles and 4 rolls of roofing paper for $10.40. In a second purchase at the same price, the contractor buys 8 bundles of shingles for $256. Find the price per bundle of the shingles and the price per roll of roofing paper. Notice they have given us our 2 unknowns. I'm going to call B the price per bundle of shingles and R the price per roll of roofing paper. This one's actually really nice because we've made 2 separate purchases. In our first purchase, we bought 30 bundles of shingles and 40 rolls of roofing paper for $1,040. In other words, the $1,040 is equal to 30 times whatever the bundles cost and 4 times whatever the rolls cost. Our second purchase, we only bought bundles of shingles for $256. Let's see, it was 8 bundles, wasn't it? The cost for order 2 is 8 bundles at $B each. So it's $256 for 8 bundles. Notice once again, you have 2 equations. That is enough to make a system, and we can solve this system by graphing. Notice my first equation I solved by intercepts. I'll be honest, I actually used a calculator here because 1040 divided by 4 wasn't fun, and if I put a 0 in for r, doing 1040 divided by 30 was even less fun. But when I graph those intercepts, I get this line. Every point on that line is a possible combination of rows and bundles. Now you'll notice that some of these are fractions and decimals, which are less helpful than other pieces of information might be, but for the moment we're going to hold on to that. When I graph this, since it's a single variable, I can actually solve this and I get b equals 32. b equals 32 means my bundles cost $32. Since my bundles are on the x-axis, this is essentially the same thing as x equals 32, which is a vertical line. Notice, out of all those points, there's only one point where my two graphs overlap. That's the point 3220. That's the solution to the system, and it means that the only way both of our two stories or scenarios can be true is if they spent $32 per bundle of shingles and $20 per roll of roofing paper. I hope this has been helpful to you. As always, thank you so much for watching. Make sure you like and subscribe and leave us a comment in the comment section. We are going to talk about 2 more different ways that we can graph a system of linear equations. So make sure you check us out and come back looking for those. As always, we wish you the best of luck. You guys take care, all right? Bye-bye.